Today we're going to study this linear detent mechanism that you can add to your repertoire. Simply pull, retract the head, and put the next head on, and it stays on. How does this mechanism work? In addition, the second thing I'm going to teach you in the video is how are all these components able to stay together when we have no glue, no threads, and no fasteners. I'll show you next. This video belongs to a playlist called the Mental Mechanism Library, in which we're going to study products all around us, figure out how they work internally, and save their mechanisms in our Mental Mechanism Library. This is going to make you a better mechanical design engineer. Before we dive into the CAD, I want you to take another closer look at this mechanism, and I turn on my flash so you can see what's happening. You pull back the color, it automatically disengages the head, which I'm touching with my left hand. It becomes loose, and you can move it out. So then this is spring loaded, and what we see happening is that when the color moves in that direction, it's going to push the ball bearing in that direction inside, and that ball bearing, when it comes in contact with the detent in this detent mechanism, that's what's going to lock it in place. But that's obvious, you can see that with the naked eye. I really wanted to see what's happening in here. Where is the spring? How did the designer manage to have a spring in here? Because I can't take this apart. If I take it apart, I'm gonna break it. So thankfully I have the CAD, because we designed this in-house, and I'm gonna be able to show you what's happening in here. Stay tuned.
Sometimes the most simple mechanisms and assembly methods are what gain my admiration. Here we have the CAD model, the assembly of the device, and I'm going to make some of these transparent so you can see what's going on inside. I want you to pay attention that there's this shaft, inner sleeve called, and this is going to help you understand how everything is assembled. As you may notice, without threads, without glue, no fasteners, how do these parts stay together? So let's isolate the sleeve, and I want you to pay particular attention to how it's made, how it's manufactured. It's got these V-shape extrusions, these teeth, if you will, and the way that it's all assembled is that it's press fit. So if we exit the isolate mode, I want you to understand that let's remove this part and that part. Well, in fact, let's isolate him and him. So you and you, isolate. The inner sleeve was press fit into the body, and when it was press fit, it will cut into the teeth in such way that it'll be almost impossible to get the sleeve out. And on purpose, the teeth are made because it won't allow for rotation. Once the teeth are clenched in, if you will, you can't rotate it. Then the other thing I want you to take into account is that we need to do a cross section for this. That's good. And we need to look at it from this side so you can see the cross section. What's holding it all together, first what's holding the yellow part together is the inner sleeve is constrained, but it's almost sandwiched, if you will, between this wall that we see here. Select other, one of my favorite shortcuts. This face is coming in contact with this face, so it's locking the yellow part in place. So the yellow part is immobile. Now we see a spring. The spring is extended, but in reality the spring will go from this face here up to this face here. So now it's expanded, but it'll be compressed. So the spring is constantly trying to expand and push the red part off to make it slide off the sleeve, if you will. So why is the red part not sliding off the sleeve? It took me a little while to get this. If you get this, you're probably smarter than me. It took me a little while, but when I got it, I realized that the sleeve part, the red part, is being pushed to the right, but it will stop because it's like a wedge here coming in contact with the ball, right? And the ball is not able to go all the way through and fall into the hole on the inside because the diameter of the ball is larger than the orifice right here. And let me remove the cross section so you can take a look at what I just said. That's the beauty of SOLIDWORKS and CAD, that we can zoom in to very small places. This is what I mean. The orifice is smaller than the diameter of the ball, and that's why the ball can't fall through. And I just thought that was a magnificent mechanism to reduce the amount of fasteners and the assembly time. Anytime you can reduce assembly time, that makes the cost of production cheaper. So I think that was pretty clever. This was designed here in-house at teampipeline.us where I work, and I really enjoyed studying this mechanism. If you appreciate the content that I'm sharing, please like, comment, subscribe. My name is Rafael Testai.